Hello everyone, this is the part 2 of how to use ADC in FPGA using Xilinx system generator. Okay, in previous video we have seen how to configure the XADC Wizard block. Okay, and we have discussed in detail, so please watch it before. Okay, now let's move to the second part. And in this video I will tell you how to make a MATLAB simulation file. Okay, so procedure is simple. What we do, first we make a simulation file. Okay, first we make a simulation model. Okay, simulation model, then generate this simulation model is generate IP catalog. Okay, IP catalog is basically a block form in Vivado. Okay, and this IP catalog block is connect with XADC Wizard. Okay, and this whole combine by combining this IP catalog and XADC Wizard, we generate ADC, means we do analog to digital conversion. Okay, and we have another process where we generally do not use this Xilinx. We have second process in which what we do, we generate the same Xilinx model, generate IP catalog. Okay, IP catalog, and after generating IP catalog we generate a code, Verilog code for this Xilinx model. Okay, we generate a Verilog code for this Xilinx model. Similarly, what we do, XADC Wizard, we have a XADC Wizard, we generate same Verilog code from Vivado. Okay, Verilog code, and these two code are merged together. Okay, merge means we connect this XADC and IP catalog through Verilog. Okay, and after this we can make our analog to digital conversion. Okay, so in this video we will discuss only this part where we make a simulation model, then generate IP catalog from system generator, and after IP catalog generation we make a XADC Wizard and then connect it and make according to our desired ADC conversion. Okay, next I open MATLAB Simulink. Now I have opened a simulation model, so don't worry, I will tell you each and every block. I have opened a system generator which is connected to my 2017 MATLAB. Okay, so in previous video I gave you one example with boost converter. Okay, where I sense the output voltage and using the controller we control the output voltage. But for understanding in this video I will tell you I will give you another example where we are what I am doing in this model I will tell you, but this is the different example than the boost converter. So this is here you can see these type of blocks are system generator block, Xilinx blocks. Okay, so where you can find this, so first of all you need a licensed version of Xilinx. Okay, so I have one. So here you can see this MATLAB is similar to any other MATLAB where where you can find each and every blocks such like in regular MATLAB. But one thing is different from the other in system generator. You can see here you can see a left corner. I am expanding this. In the left bottom corner you can see Xilinx block sets. Okay, Xilinx block set where are different types, where first is XE4 where you can see I am zooming. Okay, so no zoom in. Okay, so you can see first is XE4 where you can see different types of blocks. Basic elements block where you can see a basic elements block, system generator, absolute. So very limited blocks here compared to regular MATLAB. The Xilinx block sets are very limited. So with this limited block you have to design your model. Now okay, so I hope you understand this. Now moving to what simulation, this simulation blocks, what I am doing. So first of all, when you make a using the Xilinx block set, so first of all you have to consider, suppose this is our model, okay, and this one is gateway in. It means whatever inside this gateway in and this one is gateway out. So whatever is between the gateway in and gateway out, those blocks are converted to IP catalog, means Verilog code, okay, and outside this ADC, outside this gateway in and gateway out will not generate any code, okay. These are simple MATLAB blocks where you can see sine wave, constant, this is a constant block, this is a add block, this is scope. And one more thing unique required is system generator, okay. It's something like we use Power GUI in regular MATLAB. Now come to this model. So what is the logic behind this MATLAB simulation? So I have make a logic where suppose this is my sine wave, okay, this is my sine wave. So what I have made here, if for positive half cycle I want to generate a pulse for to switch, okay, if the sine wave is positive, then I generate a pulse, train of pulses, okay. Train of pulses means for positive half cycle there are different okay. So for positive half cycle I generate a pulse which for switch 1, okay, and for negative half cycle I generate for another pulse for my another pulse for negative half cycle, okay. Sorry, for negative half cycle means for 10 millisecond I generate this pulse, and for another 10 millisecond means this is a 50 Hertz cycle. 50 Hertz means 20 millisecond time period. For 10 millisecond for switch 1 and for 10 millisecond switch 2, okay. This one is for switch 2, okay. So I hope you understand what I am doing here, means generating pulse for positive half cycle and generating a pulse for negative half cycle for different switches, okay. Now you can see first of all you can see I am generating a sine wave, okay, sine wave which have the amplitude of 0.4, bias is 0 and the frequency is 50 Hertz in Hertz, but we have to convert in radian per second, means 2 pi f is 50, and the sample time, this is not a Xilinx block, so you can keep it as it is, so no change. So why I have add 0.4, since our signal is how much? So by using sine wave we are generating a sine wave of how much? This one is 0.4 peak and this one is 0.4 peak, okay, means peak to peak is 0.8, peak to peak is 0.8. So as we know microcontroller, we have to shift this means whatever the signal is there, we have to shift it above the 0, and different microcontroller have limited value. For peak to peak value is limited, means in this case the peak to peak value is how much? 0.8, okay. Like in FPGA you can give ADC pin less than 1 volt, okay. If you give more than this, then your FPGA may get damaged. So for safety reason I gave voltage of 0.8 peak to peak. Okay, so what I have to do, I have to add a DC signal in this sine wave to shift this sine wave above 0. Okay, so I have added 0.4. You can see in simulation I have added 0.4 to the sine wave. Okay, it means whatever the bipolar nature of sine wave, it shift to above and make it unipolar. Okay, then I have used gateway in block, where you can see I have used signed, and the number of bits I have used is 12 and binary is 11. So I have discussed about this in previous videos, what is binary numbers, so you can watch. Now this one is relation, means comparator with constant block. It means you can see the value 0.999 means almost 0.4. Okay, if I open this block, you can see I have gave a 0.4, but according to the bits, it get automatically updated how much value possible with these bits. The Xilinx block automatically adjust. Okay, now if you understand this, if you see it, this block is trying to say that if the signal, whatever signal is coming here, is more than above the 0.4, means if you see this is our means this is the 0, this is 0 and this is 0.8, and the average if you take, means mean value is 0.4. It means if my value is above 0.4, which is representing here 0.4 representing here 0 line. Okay, so if the signal is in A is greater than B, then it gives a signal of what you can see output is boolean. Okay, if the condition is true, then the output is 1. If the condition is false, then the output is 0. Okay, now you can see in this block what I am doing is a counter is there and constant is there. If you see in previous video, I have discussed about what this blocks making, means it simply make a pulse signal. Okay, means this is a counter and compared with constant block. Okay, and compared with this constant block, then it will give a pulses. Okay, this pulses is going to this mux, all this mux and this mux as well. And similar type of block I have made here, which is in this case, if the signal is which is coming from this ADC, if the signal is less than these constant blocks, means below the it means negative cycle. This one is for positive cycle and this one is for negative cycle. If this negative cycle, then this will activate. Okay, this one is continuously generating pulse. Okay, these three blocks continuously generating pulse, which is coming to this mux and this mux 1 in a D1 point. Okay, now this constant is 0 value, this constant is also 0 value, which is coming to D0. So this one is select line. Okay, which is coming from this comparator select line. If the select line is 1, then what happens, the D1 will select. If the select line is 0, then D0 is select. It means if my condition is true, this condition is true, the select line is 1 and the output which is coming to D1 is the output of our mux. Okay, similar to if the select line is 0, then the D0 point, whatever the input in D0 which is coming out. Okay, similar to above condition, same thing is happening here. I am adding the input as well and time for 0.1. Okay, so again I am running this block, so don't worry, this one is warning for I am using this using this MATLAB blocks, that's why it giving some warning. So don't worry, stop and open this. Now you can see the input is coming from coming to ADC is 0 to 8 volt, means peak to peak is 0.8. It means 0.4 is our mean, and above 0.4 is similar to positive cycle, and below 0.4 is negative cycle. Okay, now for positive cycle means above 0.4 this switch is on and this is switch is off, and for below 0.4 this switch is on. These are the train of pulses, means there is pulses, many pulses. Okay, you can see. So these are the train of pulses which is turning on and off for positive half cycle, and similar to negative half cycle, the signal, the switchings are happening in negative half cycle. Okay, I hope you understand what we are doing here. Okay, this one is for understanding, which I am sensing the real value through sensor and giving to ADC. Okay, I am sensing the sinusoidal signal here from the sources and giving to ADC. Okay, and this ADC is compared with these blocks and giving output of for positive half cycle and for negative half cycle. Okay, so I hope you understand. Now save the project. Now our simulation is completed. Now I have to generate into IP catalog. So first of all, open this system generator, and I have told you how to configure this as well as. So you have to add a part number. So in my case, my FPGA is RTX 7 and X is 7A 100 clock frequency, and CSG 324. So select, and compilation I am generating in IP catalog, and the hardware I am choosing is Verilog. So and now you have to give a path for project. So try to minimize this path. Okay, so don't make unnecessary folders and try to minimize the path. So I have made a path in ADC. Okay, so I have selected a path which is okay, not the path is not longer, and the clocking is 10 nanosecond, and the simulation period is -8. Now I want to generate. So now you can see the file is generating, checking its compilation states. It will take some time according to your system or your file. Okay, this warning is similar. I am using this MATLAB blocks, so it giving me regular warning. So don't worry, it will not affect our code. So you can see generation is completed. Okay, you can see detail, but not required for us. Okay, now the file is generated, IP catalog file is generated. Now you have to go to the file where you have generated. Okay, so you can see I have generated file here in ADC where different types of file are generated with that. So you don't need to know what these files are. So our important file is IP catalog. Okay, so open it. You can see a file made of what ADC block, which is your Vivado project. Okay, this one is the main file. Okay, so I am opening it in. So directly you can open So I am opening it, so it will take time, so have patience. Vivado is opened and it's updating the file. Okay, now you can see in project manager there is a design source, okay, where our MATLAB file name is ADC for, I am giving ADC for YouTube. So this one is the block IP which we have generated. Okay, so double click. Now this is the IP block which is generated. Inside this block we have made our MATLAB simulation, and our logic is inside this block. Okay, and you can see I have told you, you can see this ADC is input and this gateway out is output. Means gateway in, one gateway in means one input, and two gateway out means two output, and one more thing input is clock. So we have to give a clock which we give which will run this system. Now what we have to do next is we have to add XADC. As I have told you, we have to add ADC. This one we have understand how to configure. We will tell you in this video as well how to configure it. Okay, now moving to, so this one is add IP, so click one and search for XADC, double click. Okay, okay, this one is XADC, so we have to configure it, so double click, and interface option we are using dynamic resistors, okay, not using XC4 light, so choose dynamic DRP, and we are using single channel. So in this case we are using single channel. For multiple channel we will do in further videos. Okay, and we do not need a reset, so untick it. ADC, do not change anything. Alarm, I am not using any alarms. Single channel, there are various types. So for our we need a VAUX. You can in previous video I have told you 4 ADC pins you can use in my case of FPGA we can use 4 ADC pins, VAUX 2, 3, 10 and 11. So I am choosing VAUX 11. Okay, so summary you can see, and click to OK. So you can see our input output ports are reduced. So if you expand this SDRP, you can see it gave me an instruction to expand, so I am expanding it. Okay, you can expand all these things. Now we have to configure it, so I have already told you. Now this ESC is connect to DN, and we need a constant blocks, so type constant, double click, constant block, and this constant block I am using 1 bit and the value is 0. This block is connected to VIN and VP. So the extra things we do not require, which I am giving input to 0, it means disabling this VIN and VP. And also this I am not writing anything, so also giving 0. Now I need one more constant block, so copy it and paste. You can take from this also and paste. So this time I need 16 bit and the constant value is 0, which is connected to this DIN. Okay, because I am not giving any input, since it is a 16 bit, 150 means 16 bit, so I am choosing the bits of 16 and the constant value is 0. Okay, one more block is required for data address. Okay, so Control C, constant copy, Control V, paste. Okay, now this time address is how much? 7 bit, and the constant value means constant value of the VAUX is 1B. I have told you in previous video, constant value is 1B in hexa, so in decimal value its value is 27. Okay, so this constant value you have to put in decimal, sorry, okay, decimal. Okay, so 1B of hexa in 7 bit is the decimal value of 27. So I am connecting to data address. How much? 6 bit. I am using 7 bit because the data address width is 7 bit. Okay, and the rest things, this one is input of ADC, so I am simply making external. It means simple a wire, make external. Okay, and let me see. Okay, now we have to connect this clock and this clock in same, means clocking of this block and this block is same, and all blocks are connected. We do know, okay, one thing, okay, output, we need output. Okay, so this one is wire and this one is input to our ADC. Okay, gateway in, so we have to add this output to we have to giving this output value to our ADC. So first of all, delete this wire. Okay, and connect. So I need only 12 bit, and the output of this DO out is the output of XADC, and the bit is 16 bit, so I want only 12 bit, so we have to add a slice. It means it reduce the number of bits. Okay, slice block. So input is how much? 16, sorry, 16, and we need only 12 bit, so I am using the MSB. Okay, there are two things, MSB and LSB, so I am taking only MSB bits from 15 to 4. Okay, and the 3 to 104 bits I am discarded and taking only MSB bits. Okay, so MSB bits I have taken, so click to OK and connect this DO block to DIN. Okay, and this from this slice block, output is 12 volt is coming to our MATLAB system generated. Okay, this one is optimized routing. If you click it will optimize and looks pretty good. Okay, I hope we have completed. Let me check once more. Okay, so this input is coming to FPGA. This input VAUX is coming to ADC pin FPGA, and the process inside this, and these things are inside the FPGA and coming out from DO through slice and coming to our generated block and giving output to our switches. Okay, now Control S, save it. We have to do now synthesis, so click in synthesis. Okay, and synthesis is running. This channel out is not required for single channel. Okay, this channel out is not required for single channel. If we do multiple channel sequencing, this channel out is required. But for our case, and for single channel out is not required. So still synthesis is running. Okay, synthesis is failed. So what they are saying? They are saying ADC does not instance. It means what we do mistake here. So if you face any problem like this, one simple thing you have to do means for this specific problem, I am making another block, means it's saying that ADC is not existing in this file, but the ADC is there. Now how to regulate this problem? So I am creating a block design, give some name, I am giving design only. Okay, cannot be used. So design 2, design 1. Okay, design 1. Now I am copying whole blocks, control A and control C. Okay, I am selecting and paste in this block design 1, control V. Okay, so don't worry about the routing. The wiring will not change, only the positions are changed only, and you have to delete these all files. Okay, delete our previous file, remove from project. You may not face this problem, but if you face, then you can resolve like this. Okay, remove from project. I am removing all projects. Also we do not required. So it's saying that top module ADC VD wrapper currently invalid. Okay, no problem. Now this one thing also I do not required, delete. Okay, now in design source only the block design is available, which I have generated, means made from copying the previous blocks. Okay, so if I double click, this one is the block design we have. Now what we have to do, we have to create a HDL wrapper. Okay, it means it's generating a .v file. And one more thing you can do before or later, generate output products. It means whatever this block is present here, it will create a Verilog file, overall file. Okay, generation is okay. You can see a .design for design .v file is means Verilog file is there, and this one is means top mode. You can see the parent means whatever the Verilog files or block design is we have made, this one is the parent one. Okay, so everything is completed. We have created .v file and created a HDL wrapper. Now save it, control S, and again I am trying to synthesis. Okay, so synthesis is running in top right corner. you can see. So don't worry about these blocks. You can rearrange it from till the synthesis is running. I am rearranging these blocks. Okay, so this one is looks better. Now our synthesis is completed. Okay, so we have successfully resolved our problem. Now before implementation we have to provide input and output pin. Okay, now cancel for time being. Now for giving input, there are various methods for generating the giving the inputs and output pins. You can go to the constraint and make constraint files. Okay, then using coding, means some type of codings are there. Okay, XDC file you can make, but I generally do not prefer this method. Now I prefer first of all, this one is synthesis part, expand it and come to schematic. Okay, so save before it, come to schematic and okay, so don't worry about the warning. This one is our RTL file. Okay, now you in top right corner you can see IO planning, so click it and you can see our your pins which you have used. Now first of all, this red one LVMOS 18, so we have to change it to LVMOS 33, LVMOS 33. Now this one is clock, so you have to provide clock name, which in our case is E3, and then switch. So according to your FPGA you can choose your switch. So in my case I am using G14. Okay, in Nexus 4 board. And for second switch I am giving name, I can give a name of P15. Okay, now one more thing, you have to change it to 33. Now you have to give auxiliary VAUX 11 and VAUX N11 and VAUX P11, means positive and negative. You have to provide according, you can see various reference manual you can find. Okay, so I'm directly giving A18 is the VAUX N11. Okay, and for VAUX P11 is B18. Okay, so completed, our configuration for input output is completed. You can see we have five input output ports. Okay, one is clock, two is for switch 1 and switch 2, and another two is for ADC VAUX 11 and VAUX N11 and VAUX P11. Okay, so control S and save the XDC file. You can see XDC file is generated. Click to OK and come to sources and double click. You can see this one is XDC file. Okay, either you can using this method you can make, or just I have done, or you can directly write here and control save, no problem. Okay, XDC is completed. Now come to implementation. Now click to run implementation. So synthesis is completed and implementation is initialized. Okay, this is Okay, so implementation is completed. Now after implementation we have to generate bits stream. So click to generate bit stream. Okay, okay. Now our bit stream is generated. Now in last step we have to open our hardware manager. Okay, now in final part we have to connect our FPGA, then click to open project and program this code. Okay, so now you can see this one is our FPGA. Okay, and this one is LV25 Hall effect sensor for voltage. Okay, and you can see this one is input which is coming from this transformer, means AC input which we have sensing is coming from this transformer. These 6 pins are for, since this Hall effect sensors use op-amps, so op-amps need plus minus 15 volts and ground. So these 3 pins, these three pins are for plus minus 15 and for ground, and this one is for input. This one is, sorry, this one is for this three for one for output. So I am taking from this wire output, I am taking this one is ground. Okay, gray one is ground and this one is orange is output. Okay, value. So now I have to connect this to our ADC. You can see this pin is ADC 11, this one is ground and this one is VCC. So I have to connect in this pin. Okay, so already there is a wire. So one more thing you have to see, I will tell you. Now you can see I am connecting. So let me connect first. I have connected VAUX, orange one is to VAUX 11 and ground to ground. And one more thing you have to consider here, the negative pins, but our VAUX N is still not connected. So what we have to do is VAUX N 11 is we have to connect it to ground. Okay, otherwise maybe it will not work. Now I am connecting this FPGA to my laptop. Yeah, I am connected this FPGA, you can see LED is glowing, connected to my PC. Now I have to go to open target. So you can see green in blue letter, you can see open target. Click to auto connect, click and it will give pop-up auto connect. Click to auto connect and it's connecting to server. Our FPGA is not programmed. If I program device, then click to program. Now you can see our device is programmed. Okay, and you can see LED is glowing where done is written. Now the our program is dumped to our FPGA. We have to see output.